So today we'll continue talking about the stochastic block model, in particular the symmetric two-block model, two communities. So we have n over 2 nodes over here, n over 2 nodes over here. And we connect nodes in the same community with probability p, and they cross communities with probability q. Right? And we think of p bigger than q. Almost everything works when p is smaller than q, but we'll focus on this case. So what we did, so this is the so-called stochastic bond model. So, what we did last time was we talked about what's so-called partial recovery. Right? So what this meant is we just wanted to understand when could we find an estimator that correlates with the community memberships, right? We're finding this leading eigenvector B that correlated with G, who was the true membership communities, right? So we call G a vector in plus or minus 1. The N, right? These were the true labels, the true memberships. So today we'll talk about something different. Today, because we're going to be talking a lot about semiconductor programming, and the main point of this lecture and this next lecture is to show that actually the semiconductor program relaxation that comes from XCut, motivated from XCut, from the Lumens and Lulin's algorithm, actually can be used here and works a lot better than the approximation ratio would suggest. Okay? So for this, we're going to focus on something else. We're going to focus on the question of exact recovery. Right? Exact recovery is going to ask a bit more. It's going to ask for which values of P and Q, right? For which values of P and Q is it possible to exactly recover memberships? And of course, up to global flip. Right, what is plus and what is minus doesn't have any meaning, right? This could be plus, this minus, and vice versa, but we're going to recover the partition exactly. Okay, so we saw before, right? We talked before about sparse networks, about when P was something like V over N, and Q was something like V over N. But if we want to be able to recover communities, exactly, recover every node, its membership exactly, we need at least, right? We need at least that the communities are connected, the graph is connected, or at least a subgraph of each community. Right, we need at least that the graph is connected, because if the graph is at a regime where we don't expect the graph to be connected, then there'll be nodes that are completely isolated. Right, and if there's one, there'll be many, right? If this is something that has a tendency to happen. And then we have no information whatsoever about each of these nodes, we could just very well swap those. Right, there'll be many, many of these. So we need the graph to be at least connected, right? And if you know some studying of early Shreni graphs, right, we can ask for at least for this, say, this half to be connected. Right, so this half is now an early Shreni graph with n over 2 nodes and probability p. And we know from random graph theory, it's a simple exercise actually, that for the graph to be connected, we need at least the average degree to be logarithmic. Right? So there's actually a phase transition in exactly log n over n, where the graphs become connected. Right? Here would be, since it's n over 2, we would have to replace n by n over 2, but it's still logarithmic. You still need logarithmic average degree. Right? I mean, one way of thinking about this is if you have a constant average degree, then basically the limit as n goes to infinity, the degree of the node is going to be like a Poisson random variable with mean, say, a, or a over 2 inside, or a plus b over 2 total. Right? So we'll have some positive probability of being 0. Right? So since you get more and more and more nodes, eventually you'll see a few zeros. Right? The only way that you won't see zeros on the degree, meaning you won't see isolated nodes, is if you expect the probability of a node being isolated to be something like 1 over n. Right? So that when you union bound over n many things, it doesn't happen. And this will happen, if you do the math, this happens exactly at logarithmic average degree. Right? So the right regime to look at is when P is some constant times log n over n. And when Q is another constant times log n over n. Right, so these are sort of, for asking about exact recovery, these are the right thresholds to look at. This is the regime to look at, right? And now we can ask, for which values of alpha and beta do we actually have that exact recovery is possible? Right, and so one can prove the following theorem, which I won't prove here, but we'll get to something quite similar, and I'll explain how something like this is proven. But we can prove actually that a similar, very nice stage transition happens, that if square root of alpha minus square root beta is bigger than square root t, too, then exact recovery is possible. Right, and if square root alpha minus square root beta is smaller than square root b, then it's impossible. Okay. So this is not so hard to prove. We'll get to something similar, right? But it has a sort of a nice phase transition, similarly to what we saw in partial recovery. The way you prove here that it's impossible is you can show that when root alpha minus root beta is smaller than root 2, then actually what happens is that there are nodes. There will be nodes, with high probability the following will happen. There'll be nodes that are actually more connected to the other community than to their own community. And therefore, you know, there's no way to tell that those belong to their community. You would potentially just swap them, right? To prove that exact recovery is possible, actually what we're going to do is we're going to study an algorithm that, because the proof we're going to do is going to be a little loose, like to be a bit easier to do in the lecture, and actually the proof is a bit more enlightening. We won't get exactly to this threshold, but we'll get to something maybe a factor of 2 away or something like this, pretty close to it. Right, but we'll get to something like this. Right, and of course, one thing that's worth saying is, you know, what is the natural algorithm? If we're not worried about computational complexity, then sort of the algorithm, the best algorithm is, of course, again, minimum bisection. Right? And in fact, you know, here, minimum bisection is even the natural algorithm in a much stronger sense, because, you know, if what you want to do is to exact recover the solution exactly, then one natural thing to do would be to do maximum likelihood. Right? So this is exactly, minimum bisection is exactly maximum likelihood estimation in this case. Also, if you think in evasion way, and you would like a Bayesian model where the memberships are drawn at random, and then the graph is drawn given the memberships, and then we look at the posterior of the memberships, then of course the estimator that has the most probability of succeeding is the maximum posteriori estimator. But in this case, it also exactly is the same one, right? Because there's no prior information on the nodes, they're just false positives. Now, interestingly, for partial recovery, for the problem of just getting some correlation, this would still be the natural algorithm to try, but we don't know that it's actually the one that's most likely to succeed. Nothing tells us that the maximum likelihood estimator or maximum posteriori estimator is actually the algorithm that gets the best correlation with the truth when it doesn't really, is not able to reach exactly the truth because it's in the sparse regime and not in the logarithmic average degree. And in fact, we don't understand very well for partial recovery how well this algorithm does, and we don't expect it to be the best one. But when what to do is maximize the probability of getting everything exactly right, then for sure this is the best algorithm, right? This is the max a posteriori, the algorithm that puts out the solution that has the most a posteriori probability, therefore the one that's most likely to work. And so, in fact, I mean, another way of seeing what this theorem says is that in this regime, minimum bisection exactly matches the true labels, and in this regime, minimum bisection does not. In particular, if there are nodes that are sort of more connected to the other community than they are to their own community, in both sides, then you would just, minimum bisection would just swap them. And that's basically how one gets this floor. But so what we'll study now actually is we'll study a semi-definite programming relaxation, essentially based on the idea of the relaxation from X cut from Loomis and Williamson. We're going to understand what it does in this case. Right, so the problem here is, of course, a little different. We're trying to minimize the bisection rather than maximizing the cut. But as we'll see, this actually will be quite similar, and the tools will adapt very nicely, and I'll take that opportunity to also explain duality. Right, we've seen now a few times that minimum bisection can be written simply as maximizing over plus or minus 1 to the n x transpose ax, subject to x transpose 1 being 0. Right, and we saw many different instances of doing things like, given this problem of relaxing this to a spectral problem or an SDP or something of this type. But just like how we did a bunch of times now, we also want to get rid of this constraint. Right, so what we did when we did the last lecture is we just subtracted to A a multiple of the whole one's vector. Right, and it was a multiple exactly to take it out, take an expectation. Here we're going to do exactly the same thing. I'm going to subtract another multiple just because it makes this math a bit simpler. But of course, any multiple you subtract, it doesn't change anything. And if if you subtract the multiple, you can drop the constraint, and if you subtract a bigger multiple, it can only help. To make things as simple as possible, what we're going to define the Sine adjacency matrix. Right, so B will be some Sine adjacency matrix. Right? And so what will be is we'll have Bij. It will be 0 if I is equal to j. It will be 1 if I has connected to j, and minus 1 if I is not connected to j. Right? If you think about what B is, it's simply A minus a multiple of the whole one's matrix, right? And maybe an identity, right? In particular, what B is B is 2A minus 1 transpose minus identity. Right? If in a diagonal you get a 0 from here, you get a 1 minus a 1, you get a 0. If it's an edge, you get a 2 minus a 1, you get a 0. If it's not an edge, you get a 0 minus a 1. Right, so it's exactly the same trick as we've done a bunch of times. Right, we're just taking away this constraint so that we don't have to worry about it, and it makes the analysis a lot simpler. Right, and so instead of considering this problem, we're going to consider this problem with B, and exactly for the same reason, since effectively we're subtracting such a big multiple of 1 transpose, we can actually drop this constraint. Right, because by now, B has such a negative multiple of the one's matrix that it's itself sort of enforcing this constraint by penalizing whenever it's not satisfied. Okay, so the problem we're going to look at is sort of this. This will correspond also to minimum bisection in this case, which will be we'll simply maximize x transpose bx subjects to right, xii squared equals 1. Right, this will be our problem. And now, just like in next step, we're going to look at a semi-definite relaxation for this. Right, so the goal, the idea, right, the idea will be to look at an SDP relaxation. And then, instead of studying it in terms of approximation, what we're going to do is we're going to study it in terms of recovering exactly the right solution for the random matrix B. So we're going to try to prove that with high probability on the graph, we actually get the right solution. Okay, so let's derive the SDP. So I'll take the opportunity to derive the SDP slightly differently. Okay, so here I'll do it slightly different, right? So we did it with the vectors and so on. Here I'll use a slightly different idea, but it's of course completely equivalent as you'll see. Right, so you can think of this like you're trying to maximize x transpose bx, but the problem is that this is quadratic, but this will actually be linear. It's linear on the variables xi, xj. So one thing we could do is we could say the following: well, x transpose bx, because it's a number, it's the same as its trace. Right? Now, since it's the same as its trace, we can move, the trace is invariant in the cyclic permutation, so we can move x transpose over there. So this is the same as trace of b, xx transpose. Right, but now we can call this a new variable. In fact, define this as the variable big X. Right, now that we do this, we can maximize over this big variable, maximize trace of bx, subject to X needs to be of this form, but what does that mean? X needs to be positive, semi-definite, and symmetric, right? This means it has a collective decomposition. It also needs to be rank 1. And the xi squares need to be 1, but that's encoded in the diagonal of x, right? Because xi is basically the diagonal of x, so xii is 1, right, for all y. Right, and this is exactly equivalent to that. Nothing changed. Now what we do is we take away the problematic constraint, right? This constraint isn't convex, so we take this away. So we take away this constraint, right, and we get an SCP. And our SCP is max trace bx, right? Notice how this is just like in Guman's and Williamson, right? Such that x is positive semi-definite and xii is equals to 1. Just like in Guman's and Williamson, this is something we can solve up to arbitrary precision in polynomial time. And now the question that we're interested in is, when is it that this recovers exactly the true labels, right? So when is it that GG transpose, right? These are the true labels, is the unique solution to the SCP. Right, this is the big question. Because if it is the unique solution, then we can just solve this problem. We get GG transpose. From GG transpose, it's very easy to recover G, right? We just need to take, say, the leading eigenvector, right? I mean, okay, we don't know if we recover G or minus G, but this would just correspond to a flip on the node membership. Right, and so our question now is, when is it the case? Can we show that with high probability, when P is much bigger than Q, actually the solution to this is exactly GG transpose, right? And so this is what we're going to be doing after the short break. Thank you.